Okay, so the next example we want to do is going to use spherical coordinates, and it's going to be a rather straightforward example. So let's find the volume of a sphere. How's that for a problem for spherical coordinates? So, well, let's say a sphere with radius r. Okay, so the sphere is given by, so let's quickly draw a sphere. I'm first going to plant it in three-dimensional space in the Cartesian coordinate system, So it's just going to be sitting here, centered at the origin. I don't need a big drawing because I'm not going to do much on it. So here's my picture, and this is the point R here. Do you agree? We can make it more three-dimensional like by adding this. Okay, I want to find its volume. How do I find volumes when I'm dealing with triple integrals? Well, I'm just going to calculate the triple integral over this sphere, which I'm going to call now, guess, V, of course. S is reserved for surfaces in this course. V is for three-dimensional bodies with volume. So I want to calculate its volume. I'm going to do a triple integral of the function 1 over this domain. Do you agree? Okay, so the volume of the sphere is given by the triple integral over the sphere of 1 dx dy dz. Do you agree? Okay. Now you could solve it without changing variables. You're going to have to be very careful. So for example, the x's go between minus r and r, right? For every x, the y's go from, and then you need the equation of the circle and take the bottom part, which is the root of, or minus the root of 1 minus x squared, to plus the root of 1 minus x squared. And then you're going to have to do it in the z component between the lower half sphere, which is the graph of the function z equals the root of 1 minus x squared minus y squared, in minus that root, and then the top half of the sphere, which is the root of 1 minus x squared minus y squared. Okay, you could do it. The calculations could become challenging. However, okay, so the easier way is to say, hey, this problem has clearly spherical symmetry. No matter which direction I look from, as long as I'm looking at the origin, from the top, from the bottom, from the side, from here, I see the same picture. It's completely symmetrical. Do you agree? So this calls for changing variables to spherical coordinates. Okay, so that's what we're going to do. So what are spherical coordinates? So spherical coordinates are given as follows. So I have to tell you what x is, what y is, and what z is. And I'm first going to tell you the way I define them. So it's a bit different than just simple polar coordinates. So the way I define them, there's going to be rho, theta, and phi. There are going to be two angles involved. Rho is going to be the distance, so let's write it here. Rho, okay, let's draw it first. So every point here, this is a point in space, rho is going to measure the distance to the origin. This is going to be rho. And the distance to the origin, not just on the xy plane, but in general, the distance from the point to the origin. Okay, that's rho. Good. Phi is going to measure the let's project this point. So this point is up here in the room, right? We're projecting it here. This is the projection on the xy plane. And theta is going to measure the angle to the positive x-axis of the projection. So theta measures the angle. You take the point, project it on the xy plane, and measure the angle to the positive x-axis. Clear? So rho, distance to origin, theta, angle from positive x-axis of the projection on the xy plane. Okay? And phi is going to be the angle to the positive z-axis. So this is going to be phi. So let's write it up here. Phi is the angle to positive z-axis. Okay? So given a point x, y, z, I can measure its distance to the origin. That's going to be rho. I can measure the angle from it to the positive z-axis. That's going to be phi. And I can measure the angle of the projection on the xy plane to the positive x-axis. That's going to be theta. Okay? Now, what are the bounds of rho, theta, and phi? What are the bounds? Well, rho can obviously go between 0 and infinity, right? So rho is greater than or equal to 0 and is not bounded. What about theta? Right, theta is between 0 and 2 pi. And the slightly trickier one is phi. What about phi? So we're measuring the angle to the positive z-axis. At first you might think it could go from 0 to 2 pi as well, but that would not be a one-to-one change of variables, because if you take 2 points which sit on the same z, right, their location in terms of tell me if you understand what I'm doing. If you take 2 points that sit on the same z, that have the same z, theta already fixes where they are in terms of how they circle around the z-axis. That's what theta determines. Do you agree? So if they have different thetas, they're already going to be in different places on that circle of that rho prescribes. Do you agree? Now, if you allow phi, so suppose you take 2 points which are one the minus of the other in terms of the y-coordinate, okay? If you allow phi to go all the way around, the point here, one way to say it is take phi to, let's say, be 3 pi over 2, 270 degrees, and theta to be let's look at a point, at the point which is 1 on the y-coordinate and 0 on the others, and a point which is -1. So this is the point 0, 1, 0, and this is the point 0, -1, 0. Do you agree that theta itself can distinguish these 2 points? Right? One has a theta of 90 degrees, the other has a theta of 270 degrees. Do you see that? So if we allow phi to range all the way from 0 to 2 pi, this point could be written as rho equals 1, theta equals 90 degrees, or let's look at this point. This point can once be written as rho equals 1, theta equals 270 degrees, and phi equals 90 degrees. But another way of writing the exact same point is rho equals 1, theta equals 90 degrees, and phi equals 270 degrees. Do you see that? That would give the same point. We don't want two ways to write the same point. Okay? Therefore, we restrict phi only up to pi. Only up to pi. And now each point can be written uniquely as rho theta phi. Clear? Well, except the origin, which is just rho equals 0, and phi and theta are not defined. Was this clear? I said it probably too long, but do you agree? Okay. Now, it takes a bit of geometry. I'm leaving it to you as an exercise to figure out. I still didn't write what the coordinates are. To figure out, and you need just a bit of trig-ish ideas to figure out how x, y, and z relate to rho, theta, and phi, which are given by this. And the answer is that x is given by rho cosine theta sine of phi. Y is rho sine of theta sine of phi. And z is rho cosine of phi. Okay, so this is how they transfer. For example, you can check that, right, x squared plus y squared plus z squared should equal rho squared. Do you agree? Right? Rho is the distance to the origin, so x squared plus y squared plus z squared should equal rho squared. You can verify that. Okay? Okay. So I'm leaving it to you to figure out all these relations. It's standard trig ideas. Okay. So back to our problem. So these are spherical coordinates. These are spherical coordinates. They're a bit more subtle than the cylindrical coordinates because there are two angles here. Okay. Now, what is a sphere? A sphere of radius r. So back to our original problem. Let's look here. We want a sphere of radius r. In x, y, and z, the sphere is given by v is given by x squared plus y squared plus z squared equals r squared. That's the equation of a sphere of radius r. Do you agree? Okay. What is the sphere going to be in spherical coordinates? What's the equation of the sphere going to be? Pum 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 pum. You can do it, you can do it. What's x squared plus y squared plus z squared? The root of this is the distance to the origin. Do you agree? The points on the sphere are all the points whose distance to the origin is precisely r. Do you agree? The equation of a sphere in spherical coordinates is simply rho equals r. That's it. All the points for whatever theta and whatever phi that satisfy that the rho is r sit precisely on this sphere. Does everybody see that? Do you agree? Okay. So our domain v in spherical coordinates is going to become w, where rho equals r, and theta and phi are not restricted. So phi is between pi and 0, and theta is between 2 pi and 0. This is W. Or, well, I'm confusing a bit. The sphere is this. The volume, okay, V is given by this. That's better, because we're not looking at a sphere. We're looking at the actual ball. We want the volume of the ball. This is confusing. The word sphere, I made a mistake. The word sphere is usually considered as the surface, as the outer surface. And what I'm interested in is the volume, the solid, okay? So this should be rho is less than or equal to R. Good? Clear? Everybody with me? Questions? Say something. Don't just sit there. Come on. Okay, that's good. Okay, so what do I get? So the volume of the solid V, which originally we said equals just the triple integral of the function 1, I can now write as iterated integrals where? Let's decide the order. Theta is going to range between 0 and 2 pi, d theta. Phi is going to range between 0 and pi, d phi. R is going to range between 0 and, rho is going to range between 0 and R, d rho. And what's the function? 1 times the Jacobian. What's the Jacobian? So we need to calculate the Jacobian. The Jacobian is going to be, if you look here a second, so these are x, y, and z as functions of rho, theta, and phi. It's going to be a 3 by 3 determinant of the partial derivatives of x, y, and z with respect to rho, theta, and phi. Okay? And that's a slightly tedious calculation. And in order to save time, I did it for you on a separate board. Here it is. So you can just press now pause and look at it and see if you believe it. I want to go over it very, very quickly because it just takes time to write this. Okay, and it's very standard. So here again are the spherical coordinates. The Jacobian is the determinant of the 3 by 3 matrix of the partial derivatives of each of the variables x, y, and z with respect to the new variables rho, theta, and phi. I calculated all the partial derivatives. That's this determinant. And then I solved it. How do you solve a determinant? So I chose to develop it using the third row, not row, but row as opposing to column. And it's cosine phi times this minor, this times this minus this times this, that's this, plus 0 times this minor, I didn't write that, plus minus rho sine phi times this minor, this 2 by 2 determinant, this times this, minus this times this. That's this. And then if you take out common factors and keep remembering that sine squared theta plus cosine squared theta is 1 and sine squared phi plus cosine squared phi is 1, it simplifies greatly, and this is what you have at the end. Okay? So make sure you're okay with this calculation. You don't need to do it again and again. Okay? So the Jacobian is minus rho squared sine phi, and what we need is the Jacobian in absolute value, so it's rho squared sine phi. That's what I'm going to write here. 1, let's erase the 1, rho squared sine phi. This is just j in absolute value. And this is what I need to calculate. Okay? The calculation, again, is not difficult. So what do I have? There are no thetas here. Well, let's do it appropriately. Okay, so the integral from 0 to 2 pi d theta of the integral from 0 to pi d phi, and then I have rho squared times sine phi integrating d rho, so I'm going to have sine phi times rho to the power 3 over 3, evaluated between rho equals 0 and rho equals r. I'm going to plug in r. I'm going to get r to the power 3 over 3, pull it all the way out of the snake. R to the power 3 over 3. When I plug in 0, it gives nothing. And then I have here the integral from 0 to 2 pi d theta of the integral from 0 to pi d phi. And all I have here is sine phi. The antiderivative of sine phi is minus cosine of phi, evaluated between 0 and pi. And all of this I'm integrating from 0 to 2 pi d theta. And then there's this r to the power 3 over 3 out here. Now let's be careful. Cosine of pi is negative 1, but there's this minus here, so it's 1. Minus plus cosine of 0, which is 1. So this entire thing is a 2. So I'm pulling it out of the snake, 2r cubed over 3, and then I have the integral from 0 to 2 pi d theta. This is just the function 1. Its antiderivative is theta. When I plug in 2 pi, I just get 2 pi times this. And that just gives 4 pi r cubed over 3. And you may have known that this is the volume of a sphere, of the solid, of a ball. Okay? Did you know that? Oh, good. Whew. Okay. So if what I did in terms of the calculation was too speedy for you, then just do it on your own. Don't get intimidated. Just do it on your own, and you'll find that it's going to take you maybe 60 seconds more. Okay, it's sometimes harder to follow somebody else's thinking than just doing it on your own. And if you do it on your own, it's really easy. You're going to do it probably as fast. Okay? Okay. So this wraps up this example. I want to do one more example of changing variables. And the last example is going to be what we called ad hoc-ish. So I'm gonna rather than use standard spherical coordinates or cylindrical coordinates, I'm going to use some change of variables which is really set up for a specific example. And the idea is to try to see how we get those kinds of things. And we did an example, in fact, with double integral. It's going to be along the same idea. We're going to calculate, instead of j, we're going to calculate j inverse, and that's going to be 1 over j. Remember we said that? The j inverse is 1 over j? Okay, so that's coming up next.